Yo gamers, it's time for another vector spaces / linear algebra video. I'm standing a million miles away from the mic, there we go, then the webcam scuffed. Oh boy, we move. Okay, so we're doing more linear algebra stuff, and now we're going to do chapter 7 of the main branch of stuff. And we're just going to jump as soon as possible into a worked example, where we're going to look at linear transforms, and we're also going to look at transform matrices of linear transforms. That sounds good, stick around. But before we do that, I just wanted to quickly make sure everyone was on the same page, because the definition of a linear transform is quite straightforward, and just so everyone's up to speed, we're going to do a quick bit on the definition. It's hopefully only going to take about 3 minutes, so if you already are happy with this, you can skip ahead about 3 minutes in the video, and roughly you can scroll ahead until you get to this colour on the screen again. But for those of you that want the recap, I'm going to try and do this really quick. I'm going to set like a 2.5 minute timer so I don't spend too long on it. Okay, so a linear transform, essentially it's a function, and in order to describe it we have to have two vector spaces, v and w, and critically these two vector spaces have to be over the same field. It doesn't matter what the field is, could be reals, could be anything else. So we've got two vector spaces, and we say the function t from v to w is a linear transform, and other names for this is linear transformation, linear mapping, but you'll see these elsewhere. I tend to use linear transform just because it's a bit quicker to write. Anyway, so it specifically, this function is a linear transform when for all v1 and v2 of v, and for all lambda of f, we have that t of v1 is of the set w, which is kind of already given in the definition, but I wanted to include it as a bullet point just to make sure this point's clear. Sometimes in calculations, sometimes you like loosely forget this, because here we haven't said anything about the dimensions of v and w, so they can be different dimensions. So it's worth like noticing the output's going to be different to the input in terms of the size of the vector is generally what this means. But we'll see that in a second, so don't worry about it. It's not that important to the definition. In fact, it's already given here, but I wanted to include it here. The other two, though, let's do it. Is you've got t of v1 plus v2 equals t of v1, and this is true for every v1, v2 of v, plus t of v2. And notice here, it's a small detail, but here we're adding vectors from v. So this is the vector addition with respect, maybe we'll do subscript v with respect to v. And here, what's this t doing? Didn't even click that. Got 30 seconds left. I guess I can spend a bit longer. We'll do maybe a minute, 15 more. So there is addition with respect to v because we're adding v, but here these are both elements of w, so here we're doing addition with respect to w. So you don't actually need to worry about this in algebra and proofs ever, or that much at all. It's just bearing in mind these additions are two different additions, and so this is actually quite a critical key defining property. This isn't trivially true of any function t from v to w, so this is a defining property because it's for all v1 and v2 that will make sure that by definition this is a linear transform and not just any old function. And then finally, let's just look at the final one. And similarly here, this is addition scalar multiplication with respect to v, and outside it's scalar multiplication with respect to w. But again, you just kind of have to use this exact algebra expression type thing, and this is a property you have by definition of it being a linear transform. And that is it. So now you should be all up to speed. If this was a bit too fast, this is going to be episode 5 of chapter 4. And we're going to do an episode 4, which will be, oh no, this will be episode 6, I think. I don't know, you can see in the title which episode it is, but I think the episode before this will be some easier worked examples, and the episode before that will be this theory, but done a bit more thoroughly. So if this was a bit fast, you can maybe go back to, write this really quick, back to episode 4 maybe, but I think this was pretty clear. This is the definition, and I think a lot of people saying this would have already seen this. Alright, worked example time, shall we? So we're going to try and do 4 examples in this video, but they're going to be quite related, so we're doing them all in the same video, and we're probably going to be comparing between them at the end to try and get some insights about transform matrices. Is the main thing we're trying to figure out here. So for this example, there's a fair bit of text, but not too much, and there's going to be 2 extra lines I'm going to write as we get there to keep this a little more engaging. I guess we'll just quickly read it. So what we're doing is we're saying let v equal r cubed, let w equal r squared. So we've got two vector spaces, and these are going to be over the set of reals. That's not a real, because we've got real vector spaces. So all our scalars are going to be real numbers. So we've got v equals r cubed, w equals r squared, and we're saying let t from v to w be a linear transform, meaning we get all the properties by definition we just looked at. And then also we have that it's defined like this. There are a few ways you can define a linear transformation. You can define it by showing for each basis vector. What should we call it? Yeah, let's just call it I equals some vector. And you could do this, let's say you've got, in this case we do have, but let's say we're going from R3, don't know, for a different example, maybe to R3. One way you could define a linear transform is you could say, for each vector, for each basis vector, where does it go? Another way you could define it is like this, just give the expression, what it does to the coordinates, to give you an output. And notice here, this is giving I'll write this here actually, maybe. This is giving something of R2. So we're putting in something from R3, we're getting something from R4, R2. So we're going from R3 to R2 as discussed. And so there's three ways. One, you could do this. Two, you could just give the expression. And the third way you could do it, which we're actually going to do for this transform, is you give the transform matrix for the linear transformation. And the transform matrix actually gives us slightly more information than this, as we'll see. And we'll get into that more, don't worry about it for now. So there's the linear transform we have in this case. And now we're going to say let BV be an ordered basis of V. And in this case it's actually going to be the standard ordered basis, so I could have put the standard if I wanted here. Maybe we'll edit that in here. And it's a standard basis, so the first one is 1, 0, 0, 0, 1, 0, or 0, 0, 1, and we've labelled that V1, V2, V3. And that's our basis for V, which has three vectors because V is three-dimensional. And now we're going to write out what we're going to do for W. So we're going to say let BW be, we'll put an, but it's going to be the standard one, but we're going to write it out. So be an ordered basis of W. And the key thing is that this process we're going to do is going to work for non-ordered bases, as long as it is a basis. So ordered set BW equal, and remember W is R squared, so that means we're going to have two basis vectors. Let's remove these arrows now. So we're going to, because it's an ordered set, usually sets aren't ordered, but because it is, we can do this to assign W1, W2, just a short little trick to make writing a bit quicker. So now we have W1 is 1, 0, and W2 is 0, 1. So, as you know from how these work, is if I was to, what's an example of this? Yeah, no, just, oh, I know. If you have like the coordinates 4, 3, the way the bases work is I'm sure you know, is you can do 1, 4 times 1 plus 3 times 0. It's just the standard idea of standard bases. And this property works very differently if it's non-standard bases, but for standard bases you have this property. It's like an extra property as long as they're standard bases. Alright, I think we've digested the question. Now let's actually look at it. We need to find the transform matrix of T with respect to BV, BW. And this with respect to is just a common thing you'll see. Transform matrices not only encode the transform T, but it also gives how T works with respect to some bases, and these don't have to be the standard bases. And indeed, as we'll see, the transform matrix will change if they're not the standard bases. And I'm omitting worked example E.4 for now. We'll come back to this. It's going to be based on this same saying, but I think it's better just to do the first part first. So let's just do that. Solution to E.1. So there are a number of things we could do to try and get the transform matrix. Obviously I haven't given you the definition of that, so I'm going to have to just show you the way that's sort of a good way to do these. There's probably other ways you could find, but this is a pretty efficient way, so I don't see any reason to stray from it. All you do is you take every basis vector that you've been given for the domain, which is V, or the inputs. So in this case we have, we have V1, actually I did a take, we'll do that. V1, V2, V3. So what you do is you apply T to each of them. So we do T of V1, we do T of V2, and then in a second we'll also do T of V3. and you see what you get, and you use this to write out the encoding of your transform matrix. So let's first of all just do it, right? So T of V1, that is T of 1, 0, 0, because we've got V1, V2, V3 are just the standard bases. The standard basis vectors. And I'm also going to copy T's definition so we make sure we avoid mistakes. So we can appeal directly to the definition to get it correct. Although it's a lot easier not to make mistakes for the standard bases, and that's why generally the standard bases are used. When you work with non-standard bases, it's much easier to accidentally make a mistake. That's why we're doing it slowly with the standard ones first, so we're ready for the non-standard ones. So, as you can see by how we've defined T, let's move them, they're just getting in the way. Alright. I'll just put equals here to make it easier. So we've got 1, 0, 0, right? So we're putting in x as 1, so we're just going to pull out the coefficient of x here, right, when you substitute in. So you get 3 times 1 minus 0 minus 4, 0. So overall you're just going to get 3. Same story over here, we've got 2 plus 3 minus 1. The plus 3 and minus 1 aren't going to contribute because of the 2 zeros, giving us simply 2. So equals 3, 2. And now what we do is this little trick that we're doing over and over again. And this is actually quite clever, I think, because we know that T is going from V to W. We know that whatever we get is going to be an element of W, and what we also know is that B of W will span W by the definition of bases. So because it's a basis, we know by definition it's going to span it. Therefore, any element of W can be written as a linear combination of the vectors in BW. So we know this element of W, 3, 2, can be written as a linear combination. So that, in other words, is lambda 1 W1 plus lambda 2 W2, where lambda 1, lambda 2 are real numbers. And we're going to be using this notation lambda 1, lambda 2 a lot, so I'll just write their reals here, and then every other time it's just, we know because we've done it before. And now, what we do is we correspond, let me just write actually one more step. So in other words, lambda 1 times 1, 0, plus lambda 2, 0, 1. And now we can expand out, right? We can look at the top row, which is going to be lambda 1 times 1, plus 0 lots of lambda 2. In fact, actually this is too basic, I probably shouldn't do this, but we'll do it for this. So you see that this gives that lambda 1 is 3, right? From looking at the top row, this can be written as a column vector 3, 2. And looking at the top row, we see lambda 1 plus 0 lots of lambda 2 equals that. So in other words, we get that lambda 1 equals 3, lots of 1, 0. And similarly, this is just looking at the second dimension, right, which is 2 equals lambda 2. And if you want, you could do the vector multiplication addition here to see that this is equal to the vector 3, 2. But I think that's pretty straightforward. So in other words, we have that T of V1 equals 3 lots of W1 plus 2 lots of W2. And this is the key information we wanted, was this here, which we now have. We can work through the next two much quicker because now we get the idea of what we're doing here. And because it's a standard basis, nothing crazy happens. Not yet anyway. That comes in worked example 2. So T of V2 is T of 0, 1, 0 equals, that's going to be the y1, so the coefficient of this is minus 1, coefficient of this is 3, so we get minus 1, 3, when we substitute in y equals 1 into this expression here. And that's going to be equal to, we'll do it like this, I guess. It's going to be minus 1 times by 1, 0, plus 3 times by 0, 1. But these are the basis vectors, so we get equals minus 1 W1 plus 3 W2. And you can do it slow if you want. We did the first one, so it's the same idea. I don't want this video to be too long. This is a huge example, so well, it's 4 examples, but we're going to do all of them. So I don't know how long the video will be. So T of V3 is T of 0, 0, 1. That's the coefficients of z, so it's minus 4 minus 1. So what happens when you substitute in 0, 0, 1 into our definition for t. Minus 4 with 0 coefficient, minus 1 equals minus 4, 1, 0, minus 0, 1 equals minus 4 W1 minus W2. Okay, and so finally we can actually just get our transform matrix, and this first example will be done, which is the shorter one, but the other ones will be a bit longer, but maybe not even too long. I don't know, we'll see what happens. So this just simply gives Maybe I'll write it as a bullet point. The transform matrix for T A is going to be, we know this simply by the way transform matrices are defined, is what you do is you take the dimension of the output and you take the dimension of the input and you do it that way. So this is going to be a 2 by 3 matrix. This is just by definition, by convention. You could do it the other way and it would make the numbers, the algebra slightly differently, but this is just how it's defined. So this is from W, and then we got A is of that set such that this is from V. Sorry if that's a bit small, or maybe zoom in for a second so you see what's going on. So remember, because V was r cubed and W was r squared, we have it like this. So it's a 2 by 3 matrix, and what is it? Well, it's A equals, and we just take the coefficients. Now, a critical point here is that in general this isn't going to be the case, but here it is. So you see these numbers 3, 2 are the same as the coefficients here, 3, 2, and that's just because we use the standard bases for both vector spaces V and W. If we didn't, if we use non-standard bases, these two numbers wouldn't be the same. So which ones do we use for the coefficients? Well, critically, it's these ones here. That's not highlighting. There it is. It's these ones here that we're going to use. And I'll highlight them in all cases. Where's my V2? Oh, there it is, hidden here. So these are the coefficients we use. And let's use them, shall we? So it's a 2 by 3 matrix, and we just put in the coefficients. So here we got 3, 2. So we just put them in. 3, 2. Very nice. Here we got minus 1, 3. Minus 1, 3. Here we got minus 4, minus 1. Minus 1. And that's it. This is our transform matrix, and this is just by definition, by convention. It's always going to be the coefficients of the basis vectors. When you just do T of each of the basis vectors in the input, you'll get coefficients for the vectors and the basis of the output. It's a bit wordy, but you see what's happening. We worked for it. And it could have been a 3 by 2, but by convention it's a 2 by 3. That's just how you do it. And perhaps later in this video you'll see why it's that way, or you just will disagree with it being this way and think it should be the other way. But I think following conventions is usually a good idea unless you're an expert in the topic, which takes maybe a year or two, I don't know. Okay, because at the end of the day it's linear algebra, right? It's not like cutting edge mathematics necessarily. It doesn't mean it's not useful and not difficult. Unless there is research in linear algebra, I don't know. I don't know, let's just move on. We're doing a colour scheme change because I felt like it. So, here we go. Things are about to get real, guys, I hope you're ready. And there's a small chance I'll make either like a technical mistake or a number, like algebra mistake, and I might have to re-record this section, but just hope for the best. I should maybe take a break, but I kind of fancy powering on. Maybe after I've done example 2, I'll take a quick break. What to break though. So we've got the same T here, and we've got the same V and W, but we're going to change something so we get a different transform matrix. So this is the same T we had before. I could just show you that real quick. You can see here that's the same thing. 3 minus, I'm not even going to read it out, you can see it's the same. You can pause it if you want to check, but yeah, it's the same thing. Now we have let B subscript V star be an ordered basis for V, like we had before. But now it's not the standard basis. We're going to say let this ordered basis, which is also a set, be V star, be V1 star, V2 star, V3 star, such that it's equal to these vectors. 1, 1, 0 for V1 star, 1, minus 1, 0 for V2 star, 1, 1, 1 for V3 star. That's our non-standard base of V, and just to really give you the full works with this example, we're also going to use a non-standard basis. And of course, this will give us the process in full generality. But note, you could use W as a standard basis, and you could still do the same process. There's no reason why they don't have to both be non-standard. It's just that gives you the most broad example we can. So you see the process in full generality. I think I've said that twice now. Sorry about that. Let's do it. Let ordered set be W star equal. Remember, W is two-dimensional, so we need two vectors for the bases of W. So we have, we'll name them W1 star and W2 star for consistency, and with the star notation, and these are going to be, and I'm just choosing these according to what I've done before to try and make sure the working is the same, so I'd make less mistakes, is the theory. I don't even have my notes. Am I that confident I'm going to do this without my notes? I guess I am, we'll see what happens. Okay, so this is our question. So we've got some new bases, same linear transformation, same V and W, and we know that T is a linear transformation defined by this. And now here we're going to find the transform matrix, which I guess I'll underline, of T, but this time with respect to BV star and BW star, right? Okay, let's do it. Solution. How did I write this before? Solution to E.1, that makes sense. To example 1, 2. E.2. Okay, and as you can imagine, this is quite algorithmic. We're going to do the same thing we did before, but there's going to be a few subtle changes as we work through it. So here we're just going to take T of each of the bases for V with the non-standard bases. So in this case, instead of V1, it's V1 star. Very exciting. And now here it's going to be more important we actually say what this is. It's not just 1, 0, 0, we've defined it differently here. It's 1, 1, 0. So T of 1, 1, 0. And now I'm sure you're all screaming the answer at the computer screen, right? You can see what's happening here. Throw 1, 1, 0 into here, that's x equals 1, y equals 1, z equals 0. So that's 3 minus 1. It's 2 plus 3, right? So let's write that. It's very important not to make arithmetic errors with this, so we're going to be really slow and do it in 2 steps, just to make sure there's very small chance of us making mistakes, right? So you got 2, 5. Okay. Now this is an element of W. Maybe we'll write that here. So what this gives us, right, is that T of V1 star equals 2, 5. It must be a linear combination of the bases, any basis of W. So this basis here, and you can check this as a basis if you want, check it spans W and that it's linearly independent, but we're just going to take that for granted here. Because this is a basis, it means it spans W, therefore we can write this as a linear combination of the bases, right? So we've got some amounts, some lambda 1 of the reals of W1 star plus some amount of W2 star, where these can be negative as well, of course, or 0. Any real numbers. And so how do we find out what these coefficients are? Let's first expand out a little more. We know what W1 star and W2 star are. That's 1, 2 plus lambda 2, 2, 1. Alright, and then to continue, like we saw very briefly in example 1, we're simply going to expand this out using 2, 5 and using this as a system of 2 linear equations and 2 unknowns. So from here, from the first dimension, we have lambda 1 times 1 plus 2 lots of, oh that's a mistake there, it should be lambda 2. Sorry, so we've got lambda 1 times 1 plus 2 times lambda 2 equals 2, because that's the first dimension element here, 2, 5. And then here we've got 2, 1, oh no, got 2 lambda 1 plus lambda 2, right? So we've got 2 lambda 1 plus lambda 2, and I'll rub out that circling in a second, equals 5, because that's the element we have here. Okay, let's clear that up a bit. So we get this system of equations, and now you could do this by hand, but we're going to be doing this quite a bit, and it's more important the overall logic and algebra in general. Doing a simple equation like this, we just throw into a calculator, and when you do that, you can check yourself if you want, or with a calculator, get lambda 1 equals 8 over 3, and lambda 2 equals minus 1/3. Alright, and these will be useful to us later, so maybe I'll put a box around them so we can find them a little easier later. Oh, actually, let's actually substitute it back in, because this is more useful to us, right, is this form here. Now we know lambda 1, lambda 2, we can rewrite that, and we'll put that in a box. So we've got, this implies that T of V1 star equals 8 over 3 W1 star minus 1/3 W2 star. Okay. And we're going to do it all again for TV2. I hope you're ready for this, guys. Now, the depressing thing is I've done this about 3 or 4 times to make sure I do this without any errors, so I'm pretty certain I can tell you what V2 star is, just off the top of my head, which is really sad, but I wanted to get this example right. But yeah, you see here V2 star we define to be 1 minus 1 0. And while we're at it, try and keep in your head V3 star is 1 1 1, so we don't have to come back up here in a second. I want to make this video not too long. So 1 minus 1 0 equals, we need the definition. This bit is harder to remember. Okay. Okay. So we can check out what's going on here. So we got, we're putting in x is 1 and y is minus 1, so we can look at this to figure out what the values will be. This is going to be equal to the element of w2 given by, the element of w given by 3 minus 1 for the first coordinate as given by this definition, and for the second coordinate 2 minus 3. This overall gives us, no, we've made a mistake. It's minus y and we're shoving in minus 1, so it's minus minus 1. Minus minus 1. That gives us 4, 2 minus 3 minus 1. This is equal to, as discussed before, a linear combination of the bases gives us 1 w star plus lambda 2. Oh, yeah, that's not a 2. W 2 star. And as discussed, we know what W1 W star is. I'm not going to write it here. And I want to keep this video under an hour and a half if I can. We've got a lot of stuff to do. So you can pause the video and go for a bit slow if you need to check this. But it's the same coefficients because W1 star and W2 star didn't change. So we've got 2 lambda 2 equals 4 as previously discussed. You just look at the number here. Maybe we'll do squiggly underline for that. And this is 2 lambda 1 plus 2 lambda plus 1 of lambda 2 equals 1 from above. And then shove it into a calculator. It's 4, 1. Get lambda 1 equals minus 2/3. That doesn't look right to me. Maybe it is right. I'll check it with my other notes. That can't be right, that looks not right at all. Oh boy. Oh, this is minus 1 here. Oops. We spotted it immediately though, so I think we're still good on the no errors thing. You didn't see anything, guys. Yeah, I've got a thing where like if there are any arithmetic errors, like the numbers are wrong at any point, like in terms of the calculated numbers, I'm planning to take the video down probably, or make it unlisted at least, because I want to get this correct or redo it. So lambda 1 equals minus 2. There we go, that looks better. Lambda 2 equals 3. So as previously discussed, when we got it right here as well, this indicates that T of V2 star equals minus 2 W1 star plus 3 W2 star. Alright, one more to go. Hopefully you remembered. I probably released the question, maybe my working as well as a PDF, so that might make it easier to follow along. So you can look in the PDF, or you can just remember from the video, or maybe scroll back a little bit in the video. But it was 1 1 1, or just trust me. V of 3 star is 1 1 1. So that means we just add up all the coefficients, right? When you shove in x, y, and z into here, you're just going to add up the coefficients. So we got 3 minus 1 minus 4. So we'll write that here. 3 minus 1 minus 4. And here we got 2 plus 3 minus 1. Equals 3 minus 1 minus 4. It's 3 minus 5 makes minus 2. 2. 5 minus 1 makes 4. This equals lambda 1 w1 star plus lambda 2 w2 star. This forms a system of equations given by 2 lambda 1, no, given by lambda 1 plus 2 lambda 2 equals minus 2 from here. And this is 2 lambda 1. This is just because we know what these are at this point. The coefficients are on this side from here, and the numbers on this side are going here. You get the idea there. Lambda 2 equals 4 from here, going to here. Throw it into a calculator. You know the drill. Gives us lambda 1 equals 10 over 3, gives us lambda 2 equals minus 8 over 3. Check with the note, it's the same thing, that is good. Gives us that we have t of v3 star equals 10 over 3 w1 star minus 8 over 3 w2 star. Put it in a box. And then finally, as you can imagine, we can get our transform matrix. And here you can see it's different from just these numbers here, because 4 minus 1 is not the same as minus 2 and 3. So that's critical. That's where the transform matrix comes from. So let's write out a transform matrix, shall we? Maybe to make it extra clear, we'll bring all of our findings down here so we can very quickly see what the transform matrix is. So T of V1 equals that. T of V2, very exciting, right? It might be overkill to copy it, seeing as it's right there. Yeah, it's overkill, let's just write it. So as discussed, because we're working with the same, then let's just write what's happening. So we got T from R3 to R2, as we know. T, the transform matrix, here we'll call it M to contrast with the A. Transform matrix M of the set. And as discussed, you take this and put it there. So it's a 2 by 3 matrix, real coefficients. It's given by M equals, we just take T1 coefficients for W1 star and W2 star, it's 8 thirds minus a third. Make our 3 clear. Not for now, but for later when we're looking at this working. We've got minus 2, 3 here. And then minus 8 thirds. And this is our transform matrix, which we were required to find by example 2, right? That's what we wanted. This is what it is. In terms of using it, that's what the next part is. So maybe I'll just write that in now. We're going to do a bit of reverse engineering. We're going to refer to it as M, but it's just a transform matrix from this part. Show an example of using M on some general vector v of v to apply t to v, and then we're going to use the abbreviation WRT with respect to. This is going to be with respect to BV star, BW star, because of course the transform matrix is based on this. Okay, so we are on to the crux of this video, example 3. I decided to rewrite everything from example 2, but change this last bit here. We're just going to write out the transform matrix with respect of T with respect to BV star and BW star, all we've discussed before. This matrix M we found, and then we've written out the question again, show an example of using M on V of V to apply T to V with respect to the bases, the non-standard bases. Okay, I'm going to go through this maybe slowly, but not too slowly. So there are 2 parts to this question, really. Alright, solution. There can be 2 parts to our solution. So one is just simply a calculation we're going to do, or maybe calculation / equation, and we can do that bit, and that won't be too hard, and you can do it, and really that's it's not clear with the question. That's kind of what we're really meant to do. But 2, and this is a really key bit, is we've got to try and understand this equation and why we did it. So I'm just going to do this in a really backwards way, of just starting on the calculation/equation, and eventually we'll move towards, hopefully, kind of together. I've done this a bit, but not a lot. We're gonna try and get some deep understanding of how this will work in any general setting, not just in this setting. That's quite ambitious. Let's just begin. So the way I'm going to format this is there's going to be a left-hand side, there's going to be a right-hand side, and we can work each of them separately, and then eventually we should be able to connect them, and they should be equal. And then we're going to try and comment on what it means that they're equal. Why were they equal? You know. So, going to work on the easier of the sides first, because that seems like a good idea. Which is the easier of the two sides? This is completely new and we've not done anything like this before, but I still feel like I feel like I can do this quicker and easier, understand what's going on, so we're going to do it this way. So this is actually, yeah, it's a bit backwards. We're going to do the right hand side first. And we're going to write some equations, all of which are true, and then we're going to try and link all of them up. So, first of all, importantly, we're going to remember we had v from the question that we're going to apply t to. Let's just give it some expression. And right now, I'm pretty certain this is with respect to actually just straight b of v, but I'll get back to you on that. I'm pretty certain. Might have to record a second version of this. I think I did example 1 and 2 fine, but example 3 and 4 are really quite tricky. But we're just going to push through and hope we come up with something good at the end. Then we're just going to see t of v, right? Just apply t of v, and we're going to use the original definition we used. Not going to bother with matrices just yet. And this is just the definition, so I'm just going to write it down. If I have a PDF version, you can look at that to check this is the same, but you know, I imagine people trust me on this. We just substitute x, y, and z into it to get this. So minus 4x3. And then here we have 2x1 plus 3x2 minus x3. And so then we're actually going to, so now we started with v with respect to bv. This is with respect to bw, because remember the transform matrix, the definition in function form, right, just took you from the standard basis in one to standard basis in another. That's just how you work with regular coordinates. And now we're actually going to do a change of bases. I forgot we did a change of base in this example, so it explains the point that I was going on about just before I started this example about how we haven't really looked at change of bases. We can look at it now. It's not actually that hard. You essentially do what we've been doing the whole way through this worked example, but now we like think about it differently. This is a change of basis. So our goal of doing this here is, and we know we can do this because this is an element of W, and we know any element of W can be written as a linear combination, right, of bases. But you can do it as a linear combination of any bases. So let's just say our bases now are W1 star and W2 star. The idea of change of bases is these are going to be eventually our coordinates. So you can imagine it'll be lambda 1, lambda 2. I'm going to scribble it out because I don't know if that's necessarily the best way, but I'm just going to do it, and then we'll try and really unpack what's going on later on. Hopefully you're still somewhat with me. So what linear equation madness is going to deal? Well, we could expand it out as a system of equations, but actually the easier thing to do here, which may or may not blow your mind, is write this as a matrix equation straight up, and we're going to cross over because this will be useful to us a bit later on. So you can see, right, that these are coefficients. So if we wanted to, and this is really touching on that you really are comfortable with matrices, but I'm assuming you are watching this video. You have to be really good with matrices to do linear algebra, really. Right, you can see that this matrix times by x1, x2, x3 is going to give us the same thing that we have here. These two are the same thing. And if you want to check, you can do the matrix multiplication. You'll find you get the same thing in both cases. It's just how matrix multiplication works. But what's this equal to? Well, given this equality is true, we can look at this equality here. We know what W1 star and W2 star is, and I should probably write that just to be really clear on what the heck's going on here. I can't imagine being the first person inventing all of this math stuff. I imagine it's probably a team of people or multiple people came across this at similar times. But I don't actually know. I have to look into the history. Maybe the final episode, chapter 7, could be a history lesson. Oh, desktop with real pog. Okay, so here we got these are the same thing. So we just got, and we've looked at this a million times, right? We looked at the system of equations, lambda 1 plus 2 lambda 2. But here we're going to look at a slightly different perspective, right? Why not just have it in matrix form? Yeah? Happy? But then, right, now that it's in matrix form, as you know, does this matrix have an inverse? Let's just quickly look at the determinant of this matrix. We'll just write det 0 maybe. This is the determinant of this matrix. 1 times 1 minus 2 times 2. That's 1 minus 4 equals minus 3. It doesn't matter what the matrix is, so what the determinant is, I'll dump that over there. As long as it's not 0, it has an inverse. So we know this has an inverse, right? I'm just going to tell you the inverse in the interest of time. You can calculate it if you wanted to. Oh, in fact, I haven't even written down the determinant, the inverse. I just skipped the step, I just shoved it over here. That maybe wasn't smart, so I guess we'll have to find the inverse together here. It's really easy though. Going back to like, I don't know, GCSE maths or something. GCSE first, I don't know, it's not difficult, inverse of a 2 by 2. He says that, watch me get this wrong and just ruin the entire video. So the determinant was 1 over minus 3. And then inside the A and D swap and the B becomes a minus B. This is just what you do. And there's no easy way to check it, I've just got to be confident this is fine. 4. Yeah, this looks about right. I can re-record if this is wrong, but I'm pretty certain that's the inverse. I guess this is why revision's important, but I'm like almost completely certain it's fine. Okay, I was going to use a calculator to find the inverse, but I really shouldn't be using a calculator for inverse for 2 by 2. Alright, we continue. So then we have this thing. And now any time, this is just some general x1, x2, x3, right? This is with respect. This is some v with respect to. And I just saw ahead to how this all works. I was correct when I said this. I just got confused for a second. This is with respect to bv. So we got v with respect to vt. What we got here is, by our change of bases idea here, now this is some w, but it's with respect to bw star. So these coordinates, let's say they're 1, 2, that's not 1 across 2 up like we used to with vectors. Now this is move 1 in the direction of w1 star, which is 1, 2, and then move twice in the direction of this if we had lambda 1 equals. We had the coordinates of w with respect to bw star. If this was 2, 1, that doesn't mean 2 across 1 up, it means now we do 2 lots of this, 2 lots of this, 1 lot of that. Okay. But I think that's fairly clear. Maybe not, doesn't really matter. The point is we're going to do an equation that will result in something true, and that will help to solidify all of this stuff we're doing here. So we've got w with respect to bw star, but there's another way we can get some vector w with respect to bw star. And actually further, we know this is not only w, this is w equals t of v. So it's all connecting up, but it's not with respect to bw, it's with respect to bw star, because we did this step with the matrix. Okay, so this is our right hand. We're going to say this is equal to our right hand side, and that's complete now. So remember, we've got w equals t of v with respect to bw star. Now we've got to find another expression for that, so let's do that. And this side I think is a little bit trickier, but it should still be fine. Left hand side. And here you've all been holding your breath over this, I'm sure. We're actually going to use our transform matrix we spent all that time calculating in example 2. So, in order to do that, oh man. Okay. Right, let's say what we want. We want, we'll call it like v scuffed, right? V of this weird basis equals lambda 1, lambda 2, lambda 3. And so what we're doing here is we're doing it a different way, right? Before we had v of with respect to, here we started with v. So we had v with respect to bv, then we did t of v equals w with respect to bw, and then we simply converted change of bases. What symbol should I use for that? this is a terrible symbol, but we use this symbol for change of bases, right? Change of bases to give W with respect to BW star. Right, that was our way of doing it. So we started with a regular W, but here we're going to start our journey with V star equals this. So we're starting with, and this is with respect to V star. Okay. So, how are we going to do that? How are we going to do that? Okay, so for equality, here we've got our x1, x2, x3. So we've got to have that. So just to make sure our equations connect up, that's going to be our connecting bit. But now we're going to do a change of bases. So to change of bases, right, you do lambda 1 times v1 star. I'm just going to write that though, because in the interest of time. So remember our first one, it was ages ago, it was 1, 1, 0. Lambda 2, 1, minus 1, 0. And we know this is going to be possible because this is a v and this is the bases, it spans v, therefore it can be written as a linear combination. 1, 1, 1. Right, but this is equivalent to the equations, the vector equations. Sorry, the matrix equation. x1, x2, x3. Things get really weird here. But you do just do it like this. You can check it again to make sure. Oh wait, is this even right? Oh boy, so confusing. Oh, it's so weird. This gives it, but it's like really weird why it works. We'll try and think about why it works. Again, there's two parts to it, just the equations and then figuring out why we had those equations in the first place. Maybe we just expand it out and see it works. I mean, I want it to be clear. I know it's going to be long, isn't it? It's just a long example. Oh, right. I see why, but it's really weird. So it's because the first dimension, right? Lambda 1 times 1, lambda 2 times 1, lambda 3 times 1. Second dimension, lambda 1 times 1, lambda 2 times minus 1, lambda 3 times 1. So hence we've got these here. So these, remember by matrix multiplication, go like that. If it doesn't follow, don't worry. I'm convinced myself, so I'm going to just leave it. But you can multiply this out to check these two are the same, but they are the same. That's just some simple linear algebra, though, to figure out for yourself they're the same. So we'll just move on. Right, but this matrix doesn't have an inverse. I already calculated the inverse, so just trust me. You can calculate a determinant of this if you want. But in the interest of time, I'm not going to. It has an inverse. I'm just going to write down that inverse. So we have the, we'll call it, so v scuffed equals lambda 1, lambda 2, lambda 3 equals the inverse of this, so we get, I'm just going to write it down, the inverse of this, you can check it of course. Is it easier in decimal? We'll do it in decimal, why not? I tend towards engineering when I want to do something quickly. And decimals are awesome, I don't know why. Don't know why mathematicians oftentimes want fractions. Who wants fractions, you know? I don't know, I'm just speaking trash, I don't know what I'm saying. Let's just write it down and move on. This is the inverse. I'm so paranoid I'm going to make a mistake. It's okay, I can redo it if I make a mistake. That's what I do. I'm way too obsessed over these linear algebra things. Okay. So, inverse. Put the matrix on the side by doing inverse. Get this times by x1, x2, x2. This equals v star. And now, all this work turning it into v star means that we can use the transform matrix, if you remember that from ages ago. And we can actually just apply it directly, which is so, so cool, in my opinion. So remember here we had, how was it? We had lambda 1, lambda 2 equals that. Here, it's a little bit confusing, so maybe to differentiate between the two. I didn't notice they were going to clash It's working so much clearer than I did it the first time. I did this once before, which may have been a mistake. We'll call it mu, just to not clash. These are just still some scalars. But the reason why is there's going to be a clash notation. I didn't have this clash notation before. I don't know what happened differently. I'm obviously not confusing anything with this, but we're just using different symbols so we can reuse the same lambda we had for the left-hand side. Sorry, for the right-hand side. Now we're doing left-hand side. So now we're going to apply the transform matrix. So there's our transform matrix. So if we apply the transform, this is t with respect to the changed bases of mu1, mu2, mu3, which is equal to this. And you can check this matrix multiplication to check you get the same answer, but I did it before the video and I got right answer, so I'm happy with this. So we have that W star should probably be, I think I put the star at the top, I think that's probably clearer. Equals lambda 1, lambda 2 equals this thing. And let's just check that the dimensions add up as a start. I mean, they do because I've already done it, but just to see what's going on here. 3 times 1. So if you remember matching dimensions for matrix multiplication, we have that will output 2 by 1, which will be this, which will be W with respect to PW star. Okay, so we got a W star here, and let me just update my notation to account for this. Here we're saying, because of the change of things here, I don't think that was necessarily wrong. I think it's just clearer like this. We kind of moving towards this notation, which I think is a good thing. So these two sides in theory are the same, which is it's exciting, right? Finally, we have, this is our right hand side. Where's our left hand side? Oh, this horrendous thing. Feels like I'm structuring some fundamental theorem, and I'm really not. We're just giving a pretty little example for why transform matrices are a thing. So here you see we've done a lot of stuff, but we only had to use matrices is essentially the idea. And these two are true. You can do it in a calculator to check they're the same. And if they're not, like send me like a quick PDF or something like proving they're not equal. I'll probably take this down and redo it. The main source of error might be this, because it's the only thing I did on the fly. I guess I could check it's true live, but this video is already probably an hour 20, hour 30. Maybe in the next episode at the start I can show that they're the same by just doing the matrix multiplication. But yeah, so now that we've got the equation, this is the first part. Because remember we had part 1, find the equation, 2, understand what we're actually saying here. So what we're saying is, maybe we'll call it T star. We need a new notation, so we'll say let, it's going to be a bit confusing, we'll say let v of double star of some vector v equal the same vector but now with respect to bv star. Let w double star of w equal w star with respect to bw star. Okay, and then here what we're doing here is we're first of all applying v double star, and we'll say the process of multiplying by a transform matrix is T star is left multiplying, because in matrices you have to say if you're left or right multiplying, so it's on the left, right? Left multiplying by m. So v double star of v and then T star equals, as we discussed, w star, which we're saying is equivalent to regular T. No. Oh wow, yeah. So it's saying apply W double star to regular T of V. So that's the process we've just done. And so it's a little complex, but so T of V, right, is going to output from V, it's going to output some W, convert it to so this is with respect to BW, and then by using this function we've just defined, we're going to get some W star with respect to BW star. If this explanation isn't helpful, then you can just look through this example again a bit slow and do it yourself and check it all works out. But I think it's easier to look at a top level overview at this point. I think trying to work with the numbers is really clumsy. It's easier to create these abstract functions. I think these are a fairly clear notation way of doing things. That's not an arrow point to that, these are separate points. This is connected to that though. This is we let T star, we're just defining T star here. Let's put it over here for now. I think it's pretty clear. T star is left multiplying by M. Okay. And then on this side we've got, we're change of bases from with respect to BV to with respect to BV star, and then we're using our transform matrix which takes in a BV star and returns a W star which is with respect to W star. Hopefully given you enough there to be happy. And in fact, I'm gonna copy this equation and we're gonna use it for our final part, and then we're gonna be done. As example 4, I think we'll do it at the bottom here. This is a less busy PDF, so. Oh, I was worried you wouldn't be able to see this. You can kind of see it. You know, that's kind of clear because it's from a different document. Sorry if you can't see that. We'll be using it anyway. Alright, let's do it. As promised, our final example, we're going to apply A. Example, and this should be a little bit simpler. Example, we're finally there, 8.4. Oh, I'm kind of used to the thick pen, so maybe switch to a thicker pen. Alright, so we got our A. So as we've seen here, A is the same as our T star. This is a general formula. In here we don't actually need something as complicated as this because we had standard bases, but we might as well use it to show that it still works, right? So what this is equivalent to is we're doing, remember T star was the matrix left multiplied, and then here to change from, we're changing from B of V to B of V, right? Because we just need B of V. So therefore, to go from B of V to BV, as you can imagine, it's just the 3D identity matrix. I would explain it more, but I think people are generally happy with using identity matrices. There's a lot of theory you could describe, like proving the identity matrix does this, but I don't really care. It's identity matrix, isn't it? It's the do-nothing operation of linear algebra. So multiply this by x1, x2, x3, and this will give us a W with respect to BW. Remember, is because our changed basis and our original basis are the same, so therefore this whole equation simplifies to just this. And I think this is a really pretty way of thinking about it. And then here, do the same thing. We're doing W star, which in this case, what is W star? W star means, this might be confused, use equal sign, we'll just put it in a cloud, maybe, it's less confusing. W star is to go from BW, change of basis, to BW, right? So that's multiplying by the identity matrix. We can put, oh, in fact, we do transform of the, so identity matrix times by transform of x1, x2, x3. And given that these coefficients here are the same as the coefficients we saw inside the t function, it should be pretty clear this equality is the same. And so this simplifies down to any time, as long as you're using the standard bases, any time you want to apply t of x1, x2, x3, as you can imagine, this is the same as in this case, just a times by x1, x2, x3. But this is only if you didn't do change of bases. If you did change of bases, here's where the change occurs. You put a matrix here and a matrix here to represent changing of bases. Yeah? Okay. I think that helps sum up why these examples. So this isn't always true. This is only true if you're using standard bases. The transform matrix in this matter. If not, as we saw, you simply insert in Oh, this example. This is let me title this. Actually, I haven't got time. This is example 3. As you can see, you insert in. You simply insert in a change of bases. So this is change of bases from BV to BV star. And here, this is change of bases from BW to BW star. I think. Yeah. Okay. And we got the BW by doing T of, this is T of, and then of V. Which, of course, we've defined to just be x1, x2, x3. So, yeah, maybe wasn't, I mean, I'm pretty hopeful that was okay. I mean, at least it's a good stab at trying to make this example as clear and try and get into the deep depths of it. But if it was overly complicated, example 3 and 4, you still just have example 1 and 2 here, which give you the fundamentals, but wanted to try and really get into the nitty-gritty of this transform matrix example. So hopefully that was successful. Hopefully there's no arithmetic errors. And yeah, that was all. Have a good one, guys. Bye.